in terms of setup, are we good to have her start presenting, or are we waiting on anything?
What?
Are we good to go ahead up front, or are we waiting on anything?
We're ready.
Okay. And then, are we live as well, or are we gonna do a hand signal?
We're live.
Okay. It's not intuitive, but good. All right. Good to go.
Good to start.
Whenever you're ready.
Okay, awesome. All right, hello everyone. Welcome to the Cryosphere Pavilion. My name is Ellie Miller. I'm a PhD student at Colorado School of Mines, and I have the pleasure of being one of the early career scientist volunteers here with ICCI. I'm going to be introducing our next event, which will be titled Warming of 1.5 degrees Celsius is Too High for Polar Ice Sheets. And our first speaker for this session will be Dr. Chris Stokes, who's a professor of glaciology at Durham University, so I will go ahead and pass the floor to him.
Thank you, Ellie, for that introduction. So yeah, there'll be two speakers in this session, and I'll be talking for about 15 to 20 minutes, and then Ricardo will be speaking afterwards, and then at the end of that we'll be really happy to answer any questions that people might have. But one of the main messages of this session is placing the current warming in the context of the kind of most aspirational target of the Paris Agreement, and saying what it means for ice sheets and sea level. And what I'll be talking about is based on a recent paper that we published earlier in the year together with co-authors in the UK and in the US, which really just wanted to point out that even if we were to meet the Paris Agreement target of 1.5, or if we were to meet it after a relatively brief overshoot, that policymakers and governments still need to prepare for some quite high rates of sea level rise, that this is not going to necessarily make the problem of sea level rise go away. And this particular paper, we looked at 3 lines of evidence. We looked at current observations of change, so what have the ice sheets done in the last few decades, how much mass are they losing, but we also looked at how ice sheets responded during past warm periods, where temperatures were close to 1.5 or maybe just above 1.5. And we also looked at some numerical modelling projections as well of what happens to ice sheets at certain temperature limits. And Ricardo will pick up on that theme after my talk and look at those kind of tipping points and irreversibility and committed amounts of sea level rise. So just to set the context, I'm sure this is a figure that's familiar with a lot of people in the audience, and will be put up, I'm sure, several times at this COP and as it has been done previously. But simply to point out that today's warming is about 1.2, 1.3 degrees above pre-industrial temperatures, and that our current policies and action will take us somewhere between 2.5 and 2.9. And sorry for that, I've just lowered the microphone slightly. And what you can see on this graph is that if we want to reduce our emissions to be in line with the Paris Agreement target of 1.5, then clearly there is a huge gap between what we're doing and our pledges and where we're heading at the and where we might want to head with 1.5. So there's a huge problem here, but we really must keep this 1.5 target in mind, even with an overshoot. I think people are referring to it as the North Star, the guiding principle, the lifeline, and we really must keep it in focus. We cannot give up because it is it's a much safer limit. Every fraction of a degree really matters for ice sheets. So I'm going to skip straight to my conclusion, but there will be some slides that follow. The first thing to say is that, and the key conclusion from our paper, is that 1.5 degrees, even after a brief overshoot, is too high, and it will not stop sea level rise from ice sheets. The context here is that even under current warming of 1.2 degrees, you can see from this graph of sea level rise over the last 3 decades that the rate of sea level rise has accelerated, and that it's currently at about 4.5 millimeters per year. And if this rate of acceleration continues, and it's no reason to suggest it won't, then sea level rise will be 1 centimeter per year by the end of the century, and that commits us to 1 meter per century over the next century. So in the lifetime of our young children, we're going to see sea level rise that could be 1 centimetre a year. And that's generally seen as a rate of sea level rise that will be very challenging to adapt to, almost impossible to adapt to, in fact. You just have to move people. It's really hard to build infrastructure to protect from that degree of sea level rise. But onto some of the science then, the current observations. This animation here shows you what's happening to the Greenland ice sheet and the Antarctic ice sheet. These ice sheets together store 65 metres of sea level rise equivalent. So even if we lost just 10% of them, we're looking at 6.5 metres of sea level rise. And they're currently losing about 400 billion tonnes of ice per year. Greenland stores 7.2 metres of sea level, West Antarctica 5.3, and East Antarctica is 52.2 metres of sea level rise. And what you'll see on these animations now, which have started, is that over the last 2 decades or so, you can see that mass loss has been very much focused in Greenland and in the West Antarctic ice sheets. And these are those red areas, those hot spots that are appearing. And you can see that also from the graph that the mass loss in Greenland is much larger than in West Antarctica. And from the animation you can see that East Antarctica, which is on the right hand side as you look at the stream, it stores the most ice, but at the moment it's not losing that much ice. It's broadly in balance, but we can see some red spots kind of emerging, and we're keeping a really close eye on parts of East Antarctica because they're showing some potentially early warning signs of what we've been observing in West Antarctica over recent decades. So the observations clearly show that ice sheets have added about 25 millimetres to global mean sea level. You can see on this plot the 3 main ice sheets, East Antarctica, West Antarctica and Greenland, and every time those lines are below the dashed line of 0, it means that those ice sheets have lost mass. So for Greenland and West Antarctica, those ice sheets have been in a kind of permanent state of negative mass balance over the last few decades. As I said, East Antarctica has been broadly in balance. In fact, you can see in recent years, the black line, East Antarctica, it's subject to some weather events, some large accumulations of snow, which because it's so big, will offset some of the mass losses elsewhere. But as I said, there are also some early warning signs from East Antarctica, so that's why we're keeping a really close eye on it. But cumulatively, from these 3 ice sheets, they're losing so much ice that they've added 25 millimetres to global mean sea level, and their combined contribution is now larger than for the smaller mountain glaciers and ice caps all around the world that dominated sea level rise over the last century. So they're starting to now outcompete in some ways the smaller mountain glaciers that have been most rapid to respond. Now this is a slightly longer record of the Greenland ice sheet mass balance reconstructed back to 1850. So this is a long-term record of reconstructed mass balance. Again, look on the axis on the left-hand side where 0 is, and the black line that's going up and down is the mass balance of Greenland. The red line is showing you a kind of 5-year, and the black line is showing you a 10-year running mean. And again, you can see that this ice sheet has been out of balance for quite a long time. It's been adding sea level for quite a long time, and the blue line shows you that cumulative impact on sea level rise from the Greenland ice sheet, which has been very large, and there's been quite a dramatic drop in the last 2 decades or so, where that blue line is dropping outside what we call the standard deviations. So something really unusual has started to happen to Greenland in the last few decades. I mentioned at the start that one of the things we looked at was past warm periods. So we have times in the Earth's past that were driven by natural variations of, particularly around how the way the Earth orbits the Sun. These are very long time scale natural changes, but they provide good analogues. And there's lots of detail in this figure from the paper, but I want to make you aware that we know that if we held Earth's temperatures at 1.5 degrees, we're committing ourselves to something of the region of 2 to 9 meters. And this was very clear actually in the IPCC assessment report. This has been known for a long time, but we kind of hoped or kind of wished that actually that would take a long time. That might take thousands of years. So we have some time to adapt to maybe 2 to 9 meters of sea level rise. What we're really worried about now is that these changes are happening so quickly that we might have already triggered some of these tipping points that Ricardo will talk about within the ice sheets, and that we could see some of that multi-meter sea level rise just within the next maybe century or so. So if we look at what the carbon dioxide levels were during the last interglacial about 125,000 years ago, it's generally considered that the air temperatures were possibly lower than today, probably lower than today. Carbon dioxide levels were much lower, but sea level was 2 to 9 meters higher. If we go a bit further back in time to 400,000 years ago, this is a really good analog for a kind of near future or kind of we're already in climate. Again, carbon dioxide levels were much, much lower. Temperatures were maybe 1 to 2 degrees above pre-industrial, so kind of where we are and where we're heading this century. And you can see there that sea level was 6 to 13 meters higher. And then we had this kind of what we often refer to as a kind of near future climate state, well, the mid-Pliocene, which was about 3.3 million years ago to 2.9 million years ago. Carbon dioxide levels were actually similar to today, slightly higher. Global mean temperature was definitely higher, maybe 2 to 5 degrees C, but this, remember, is kind of where we're heading at the moment, and sea level is 10 to 20 meters above present. And that would present very challenging adaptation limits. And then that final piece of evidence that we looked at were future projections of ice sheets. And again, if you look at the literature, and there's a large body of literature where ice sheet models using different setups and different forcings have looked at what might happen to high emission scenarios or medium emission scenarios. And some of those models also run them with maybe a 1.5 degree scenario. Some of them also run with a kind of current climate state. And you might think that even under current climate, sea level rise might stop, but clearly that is not happening. So this is showing you a model that builds in some processes that there is some uncertainty around, so it tends to produce quite high rates of sea level. But you can see here, just from Antarctica alone, there's a 1 in 10 chance that it's going to add just under 2 meters to sea level rise over those timescales up to 2500. And that's it with a 1.5 degree target. And even the 2020 climate, that dashed line at the bottom, sea level rise doesn't stabilize. It keeps increasing over the next few centuries. Ricardo will pick that up. Why does this matter? It matters because 230 million people live within a meter of sea level rise. 1 billion live within 10 meters. I've used this really useful online tool to look at what would happen to the region we're currently in with just 1.7 meters of sea level rise from Antarctica corresponding to that previous plot. And one of the things that I find really interesting is that if we look at the best available science, the latest science, there is a growing body of evidence that we might be approaching, we may have even passed some tipping points with these ice sheets, i.e. that we may have already triggered something that now becomes unstoppable over the next few centuries, and Ricardo will pick this up. But even 10 years ago, people were writing papers saying that these tipping points might be approached, might be being crossed, and there's now a whole body of literature since then, some of this since the last IPCC report, all pointing towards the fact that tipping points with these ice sheets, particularly Greenland and West Antarctica, are very close and may already have been passed. So this is really worrying. And if we look at kind of the literature on tipping points, and Ricardo's done a lot of good work here with other scientists, when we reviewed the literature on this, we noticed that actually our understanding of where these tipping points lied has actually changed quite rapidly. We can go back to a paper in 1998, so not that long ago, that thought that the East Antarctic ice sheet wouldn't respond unless warming got above 17 degrees. And we now know it's much closer to 2 to 3 degrees. So I'm putting up some of the minimum estimates here because we can't rule these out. I've got the temperature plot there. The best available understanding of the Greenland ice sheet has reduced from 3 degrees in 2006 to 1.6 in 2012. And we now think it might be as low as 0.8 degrees. And as you can see from the global mean temperature graph, we've crossed this threshold already. West Antarctica is very similar. It's thought to be as low as 1 degree, but in a recent global tipping points report that was published a few weeks ago ahead of this COP, if we want to adopt the precautionary principle, then maybe we should be thinking that it has a tipping point as low as 0.5, which again, we've already crossed. So this is really worrying, and Ricardo will say a bit more about this. Just want to put up a couple of slides as well, because there's been some ideas published in the literature that we might somehow be able to slow the flow of ice from Greenland, from Antarctica, with some geoengineering interventions. And I can say that we've done enough research on this to know that these particular interventions will not work. One of the ideas is that we can somehow float sea curtains off the ocean floor that will stop warm water getting in under the West Antarctic ice sheet. But we know this won't work. We know scientifically, we've done studies that have shown that if you take water out of one ice stream, that actually you're just storing up ice that will divert the water into a neighbouring ice stream. And there are hundreds of outlet glaciers around Antarctica. We can't possibly expect to stop ice flow in one region and not expect it to turn on somewhere else, because we start changing the ice surface slopes and where the water's going at the bed, and that might lubricate another ice stream somewhere else. So there's huge logistical challenges, there's financial challenges, there's ethical challenges, but I want to focus on the science. We already know from the science we've done that ice streams are highly dynamic, they turn on and turn off, and it's largely due to what the basal water is, where it's being routed, and the ice surface slopes. And the other idea that's been suggested again is that we can drill to the bed and somehow extract water from the bed, and that this will slow the ice sheets down. Well, first of all, we know that the drainage system at the bed is really, really dynamic. So actually working out where to drill and then actually being able to find a channel that we could suck water out of would be almost impossible. We also know that the system of water is distributed across the whole ice stream bed. So these glaciers are 30 kilometers wide, and trying to somehow think we can drain water out of all of them to stop the ice, it's almost make-believe. But then even if it worked, we're just building up a reservoir of ice behind these systems that just builds up and will likely trigger an ice stream somewhere else and water going somewhere else. I liken it to a river. You know, you can dam a river and build a reservoir, but if it keeps raining, that water has to go somewhere. We can't hold it back forever. And ice sheets have a really nice system of equilibrating and looking after themselves by draining ice from them via these ice streams and outlet glaciers. But what we do know is that there is a solution out there. You know, there was a recent report showing that it is possible to overshoot the Paris Agreement aspirational target of 1.5. We maybe hit 1.7, but then we can come down to 1.5 and even below by end of century. There are some feasible, plausible ways to do this, and it requires rapid phase out of fossil fuels and greenhouse gas emissions. We will need to remove some carbon dioxide and scale that up, but it's underpinned by renewables and this kind of electrification of the systems that we use in humanity. So I think Ricardo might also pick this on a little bit. So if I just draw my part of the talk to a conclusion, ice sheet contributions to sea level rise have quadrupled since the 1990s. Even under this has all happened under 1.2 degrees of warming. Sea level rise is accelerating to rates that will be very challenging to adapt to. We're heading for 1 centimetre per year by the end of this century, which is equivalent to a rate of 1 metre per century, and that becomes very hard to adapt to. So one of the messages here is that policymakers need to understand that this problem of sea level rise is not going to go away, even if we were to meet 1.5, even if we were to overshoot and come back down to it. We still need to cope with sea level rise from the ice sheets because they take a long time to respond. And actually, the logical conclusion from this is that if we want to make sea level rise manageable, we need to actually come back down to cooler than present conditions. That's the only thing that's going to slow down sea level rise from ice sheets. But some recent work has showed that this is possible, and we do have a pathway to do that. So with that, I'll hand over to Ricardo, who will talk to you a little bit more about the tipping points within these ice sheet systems and the need to return to cooler than present conditions.
Awesome. Thank you so much, Chris. As Chris alluded to, our next speaker will be Dr. Ricardo Winkelmann, who is a polar researcher and is also the founding director of the Max Planck Institute of Geoanthropology. So please come up to the stage.
Yeah, thank you so much for the kind introduction. And I'm going to pick up some of the points that Chris already laid out for us in his presentation. And I basically want to walk you through a brief overview of what science says about tipping dynamics in Greenland and Antarctica, and about what every negotiator should actually know about tipping dynamics in Greenland and Antarctica. So we already heard that the Greenland and Antarctic ice sheets are actually among the most vulnerable tipping elements in the Earth system. And this is for multiple reasons. And I want to give you a brief overview of what these reasons are and what makes us know that these are tipping systems. First off, as a brief definition of what tipping dynamics actually are. So we say that tipping dynamics are triggered when a change in part of a system, like an ice sheet, becomes self-perpetuating. And this is due to so-called positive or amplifying feedbacks in the system beyond some critical threshold, which then leads to substantial, widespread, and often abrupt and irreversible impacts. And I'm going to come back to this definition and these particular characteristics that are laid out here in a moment. So the ice sheets, as we heard, at least parts of them, can actually not withstand temperatures of even 1.5 degrees of warming above pre-industrial levels. And that really makes them some of the most vulnerable parts of the Earth system. And if we think about it, in addition to that, it's also the polar regions that are warming up much more rapidly than the rest of the globe because of the polar amplification. So here we really have parts of the Earth system that are particularly vulnerable to temperature and precipitation changes. But the ice sheets are not only among the most vulnerable tipping elements or parts of the Earth system, but they're also among the most consequential ones. So Chris already laid out what we know about sea level rise from observations in comparison to paleo evidence, but also what we can expect in the future in terms of sea level rise. And the IPCC puts it this way, that it's virtually certain that global mean sea level will continue to rise over the 21st century. And now the question is, what happens beyond that? Because we do know that the ice sheets will keep responding for centuries, if not millennia, to come to the ongoing changes when it comes to climate change. And the IPCC says that in the longer term, sea level is committed to rise for centuries to millennia due to continuing deep ocean warming and ice sheet melt, and will remain elevated for thousands of years with high confidence. So this is really the statement that kind of summarizes what Chris also mentioned about these long time scales and the fact that committed impacts can occur. So that means the emissions right now and the warming that we're observing right now will trigger dynamics in the ice sheets in particular, which will then unfold over centuries or even millennia to come. And this is what we call committed impacts. So impacts that are already locked into the system and that are very, very difficult to reverse. And just to give you an impression of what this actually means in terms of regional consequences, because we're talking a lot about global sea level rise here when it comes to the ice sheet contributions. But in terms of regional sea level rise, when we look at the committed impacts around the globe for a scenario that's actually still compliant with the 2-degree guardrail, then you see in purple here all the areas that on the very long term will be inundated or submerged underwater. And these are heavily populated areas and would hit large metropoles like Hong Kong, Shanghai, New York City, Calcutta, and more. So keeping this in mind, I think it really shows how incredibly important it is for us to understand these long-term impacts of sea level rise, and in particular what comes from the ice sheet melt and decline. So coming back to the definition of tipping dynamics, I just want to point out a few of the characteristics that we all see in the ice sheets. So first off, our definition talks about amplifying feedbacks. It then also talks about the substantial and widespread impacts, and we've already seen what this means in terms of sea level rise. And it also talks about abrupt change and irreversible change. So starting with the amplifying feedbacks, we actually understand a lot about the underlying both amplifying and dampening feedbacks in the ice sheets as part of the Earth system. And I just want to give you one example here for a feedback that's very important for the Greenland ice sheet in particular. And that's the so-called melt elevation feedback. Because we all know this mechanism from mountain climbing. Because when we hike down from the peak of a mountain into the valley, it becomes warmer around us. Science calls this the atmospheric lapse rate. And the same is also true for the surface of the ice sheets. So if there's substantial surface melt, let's say at the surface of the Greenland ice sheet, and the surface is lowered, then at those lower elevations we'll have warmer temperatures, which can lead to more melt, which can lead to another lowering of the surface elevation, and so on and so forth. So beyond a critical level of warming, this can really become a self-amplifying feedback so that no further climate change is needed to kick this off and lead to a large-scale decline of the Greenland ice sheet. So this is an example of one of those amplifying feedbacks. And as you can see here, there are multiple of these involved when it comes to Greenland and Antarctica. And it's really the interplay, the balance of these different feedbacks over different timescales that determines what happens with the ice sheets on the long term. We also know that there's potential for abrupt change in the ice sheets. We recently actually published a review that shows some of this emergent evidence of abrupt change, in particular for Antarctica. And here you can see that on the one hand side, we have the susceptibility to abrupt change. So that's the purple plot to the upper left. But then bringing this together with the observed changes, a lot of these regions actually coincide. So this means that we are creating some hotspots for abrupt change in the Antarctic ice sheet. And for instance, the West Antarctic ice sheet is very much one of those hotspots. And this is also where we see the most drastic changes already occurring today. And we can also look at abrupt change when it comes to observations. These are some of the observations from the Greenland ice sheet. What you can see here is actually a calving event from the Ilulissat Glacier in western Greenland, which even made it into the Guinness Book of World Records as the largest calving event to ever be recorded on film. And this calving event lasted for 75 minutes. So in the span of 75 minutes, several square kilometers of ice broke off. You get an impression for the force and the energy that's in the system when such a calving event occurs. And actually, one of the scientists compared this to Manhattan, to put it basically into human scales, and said that what we see here is the equivalent of looking at Manhattan, and all of a sudden, all of these buildings start to crumble, to quake, and to peel off and to fall over in the course of a little more than an hour, just to give you an impression for the scales here. So abrupt change definitely can occur in the ice sheet, and there is emergent evidence that there's more potential for abrupt change with global warming. And we also know that to a large extent, once the ice is gone, it's very hard to grow it back. So these changes are practically irreversible. Here you can see an animation of simulations that we did with the parallel ice sheet model PISM to look at the reversibility or irreversibility of such changes on long time scales. And you can essentially see that for Antarctica, we're dealing with a sequence of tipping points, where the first one is crossed around 2 degrees, where most of the West Antarctic ice sheet actually collapses due to the interaction with the ocean. And then as temperatures increase even further, marine basins such as the Wilkes Basin here in East Antarctica also start to decline. And with even higher temperatures, the surface processes become dominant, similar to what we are currently observing for Greenland. And this is where, over long timescales, even the rest of the East Antarctic ice sheet might decline. Now, these are very drastic changes, because we should keep in mind that as long as humans have been on this planet, the Antarctic continent has never been ice-free. And we also see that even for these lower temperatures, as Chris also pointed out, drastic changes can happen, which then have really long-term consequences. We can also, with our computer models, do the reverse experiment. And after the retreat, then cool down the planet again and see if and when the ice regrows. And you can see here what in physics we call a hysteresis curve, so a huge difference between the retreat, the warming path, and the regrowth, the cooling path, with as much as 20 meters sea level equivalent as the difference between those two curves. And this is a clear sign that these changes are practically irreversible. And what you can also see is to really fully regrow the entire volume of the Antarctic ice sheet, you would have to go back to temperatures well below present day levels to regrow that initial ice volume. And even then, of course, it would be a different ice sheet configuration than we currently are seeing. So the ice sheets are subject to amplifying feedbacks, they're subject to abrupt change, and they're also subject to irreversible change. And these are the three main characteristics of tipping elements in the Earth system. And now we can even go further and look at some of the more regional changes, map out the tipping risks for each individual basins in Greenland and in Antarctica. And this is what we've done here, bringing together the likelihood of crossing tipping points in different basins with the expected sea level rise, so the volume that would be lost if that tipping point is crossed. And this, of course, brings together the two main ingredients for a risk analysis, because risk brings together likelihood and impact. So here we have the likelihood of crossing a threshold together with the sea level impact that would occur. And you can see that some of the areas that are most at risk are in the West Antarctic ice sheet, but then also some of the marine basins in East Antarctica as well. And lastly, I want to come back to a point that Chris made at the very beginning, and that is that time matters, especially when we're thinking about the discussions here at COP about overshoot scenarios. The question, what happens if we overshoot the 1.5 degree mark and then eventually get back to a safe landing climate? So, for instance, the 1.5 degrees considered as one of those. It really matters how long and how far we overshoot temperatures, especially for the ice sheets, because of the inertia and also because of the tipping dynamics. And this is one of the things that we're looking further into in TIPMIP, the Tipping Points Modeling Intercomparison Project, which not only focuses on the ice sheets as tipping elements, but also on other parts of the Earth system, including the Atlantic Meridional Overturning Circulation, the tropical forests, such as the Amazon, and the boreal forests, as well as permafrost. One thing that we can say for certain and that we can learn from the ice sheets is that because of the long response times and the potential for committed impacts, the choices and actions implemented in this decade, implemented potentially after this COP here in Belém, will have impacts now and for thousands of years. And with that, thank you very much, and we're looking forward to questions.
Awesome. Thank you so much, Chris and Ricarda. We do have time for questions from the audience, so if you have one, feel free to just raise your hand and I can come and pass the microphone around.
Hi both. Hi. Thanks so much for that. That was really, really interesting. I wondered if you could give an idea of, when speaking about overshoot, so firstly, what are the ice sheets more sensitive to? Is it the peak temperature or is it the duration of overshoot? And any idea about how long we can overshoot for before we really begin to tip these elements into really rapid rates of ice losses? Thanks.
Yeah, thank you for this question. We actually know that both the duration of an overshoot as well as magnitude play a really important role. And it's kind of the combination of both. So you could even think of them as the product, kind of how much additional heat do you put into the system. And that is what the ice sheets respond to. In terms of the timescales, we have some interesting observations from extreme events that recently occurred, for instance, in the Greenland ice sheet. So over the past decade, there have been multiple heat waves hitting the Greenland ice sheet and leading to substantial surface melt as well. And you can still see changes in the dynamics, so for instance in the speed of the glacial flow, even several years after such an extreme event. And that gives you another glimpse into what I said earlier about the timescales and how much they matter, because it's really sometimes these short instances, like an extreme event, that can have really long-term consequences. And this is what we see for the ice sheets, and therefore even a short overshoot of, let's say, the 1.5 or the 2 degree mark will have long-lasting consequences for the ice sheets. Thank you.
Is this working? I'll also just add as well, and I think Ricardo touched on this, that there are things in the system that mean just a very small change in temperature might tip, say, a part of the ice sheet margin back into deeper water that then becomes irreversible. So these systems are what we'd describe as highly non-linear. So sometimes, it's like we're rolling dice. At some point, if you keep nudging temperature up, you could tip the system and then it becomes irreversible non-linear. That might be to do with marine ice sheet dynamics. It might be to do with losing an ice shelf. So we might have a series of warm summers that get rid of an ice shelf which was previously holding back the ice flow from inland, and then that system becomes irreversible. So this is dangerous territory we're in now.
Hello, thank you very much for both of your presentations. Mine is a more political question. I'm an environmental anthropologist from Chile. And I listened to you at Bonn, Professor Stokes, when you were part of the research dialogue, telling nearly this kind of information or communication to the parties. So I'm asking you about not your best available science, but your best available experience about the communications of these facts. Have you feel a kind of different kind of approach from the parties, from the negotiators, since you are announcing or telling us about this information about tipping points, about the risk of overshooting 1.5 degrees Celsius?
Yeah, so I think I try and remain optimistic. There are parts of the negotiations where you're seeing countries very clearly using this science, using cryosphere losses as a kind of, to try and urge ambition, for example, in the nationally determined contributions. So I think there are certain parties who are very keen, very enthusiastic to use this science. But unfortunately, there are still some parties that somehow trying to downplay this. There's the risk, of course, talking about 1.5 and maybe the need to cool below present-day climate that people want to give up. But I think the message here is that, firstly, 1.5 has to be the target. We have to keep hold of that target. And then once we get to that, maybe after an overshoot, then the next discussion is, well, where do we want to land? Should we keep going down to 1.2, down to 1 degree, because we know that's a safer and just a future for people on Earth. So I think that's why we have to keep our focus on 1.5, and then we can have the conversation about kind of where we want to land after that. I don't know, Ricardo, whether you want to.
Yeah, thank you. And I think this is such an important question. So, thinking of the safe and just future, as Chris just put it, I think it's also really important to look at the regional consequences of ice sheet loss. And here I'm thinking, for instance, of the small island states, who have made it very clear that for them this is a strict guardrail that cannot be exceeded because of sea level rise and the consequences from sea level rise. And maybe just to give a positive example, looking back at the Paris Agreement, so about 10 years ago, the small island states played a really important role in the negotiations, bringing the science and bringing especially the sea level science into the negotiations. And this is also a part of what ultimately led to the Paris Agreement. So this, I think, is a success story where we can see that science really matters. And I think it's fantastic to see how Brazil and how this COP30 is really trying to put science at its center, and relate the negotiations on and base them on the scientific knowledge.
I wondered sort of to what extent has this research been expanded to kind of look at biodiversity and the impact it'll have on marine life. I'm particularly thinking kind of connection with seafood production systems and fisheries, which are obviously very material to countries' economies and probably particularly the one sponsoring this panel.
So maybe I can start on that. So we started looking into other tipping dynamics in other parts of the system as well, including marine biodiversity and ecosystems. And there you can also see that potential for abrupt change. In our review article that I mentioned earlier, there's a whole section on the risks of abrupt change in marine ecosystems in Antarctica in particular. And you can see that there really is this potential for tipping cascades, where changes in the ice sheets can trigger changes in the surrounding ocean waters that can trigger changes in the marine ecosystems. And so we really have to look at this also from a systemic perspective or a more holistic perspective, looking at the ecosystems in with the ice sheets and the ocean.
Yeah, Pam Pearson with ICCI. I wanted to go back to the original question to say that this issue of the role of science in these negotiations especially is something that we're going to be addressing in a UNFCCC side event tomorrow at 3 p.m. How it's being used and misused to some degree, especially in RSO and in the presidency consultations, to make sure that science is used in a proper way. My question is whether either of you or both of you have any comment about whether the paper that came out a couple of weeks ago on Hectoria Glacier and how quickly that receded, does this, could this be those kinds of rapid dynamics that we're afraid we might see on a larger scale, or what you think about that? Because I know there's a bit of controversy around that.
Yeah, that's a good question. So for those who aren't aware, there was a paper published a few weeks ago showing very, very rapid retreat of a glacier on the Antarctic Peninsula. And we think that there's been some sea ice and melange, which is a mixture of sea ice and icebergs in front of the glacier, kind of gluing, keeping it in place and stopping the flow from inland. And then, as you may know, sea ice is now starting to really drastically decline around Antarctica. And so the breakup of the sea ice seems to have coincided with a huge calving event where the glacier rapidly retreated. And if it's correct, and if the ice was grounded on the seafloor, this was one of the most rapid kind of events we've ever witnessed. So I think there is some debate about whether the ice was floating, in which case it's a little bit less significant, or whether it was grounding or lightly grounded. So we don't need to go into the technical detail. But I would agree that I think it gives us a little kind of foretaste, much like we've seen floating ice shelves collapse in the Antarctic Peninsula. It gives us a foretaste of some mechanisms that might play out. So one of the things we're really worried about is the role of sea ice around Antarctica. It's quite controversial. We don't know how much of a kind of buttressing force it impacts on the inland ice flow. But if what we've seen in the Antarctic Peninsula is kind of correct, then we could see sea ice declining around Antarctica, leading to some glaciers speeding up, potentially leading to some breakup of ice shelves, which then kind of releases that cork out of a bottle and allows the ice to flow more rapidly into the ocean. So it's a very active area of research. I think it's something to keep a close eye on. But I think it just gives us a little glimpse into the future of what might happen in Antarctica within the next few decades or century.
Any final questions? Awesome. And with that, we'll go ahead and conclude this event. Maybe one more round of applause for Chris and Ricarda. Thank you so much for your insights and wonderful presentations.